In an earlier chapter, we've already had the definition of a statistic, but it's an important distinction for us to remind ourselves as we prepare to do statistical inference. So when you have a number calculated from values in a sample, we call this a statistic. So statistics are measures from a sample. Some examples of sample statistics would be the sample mean, represented by x bar, the sample median, the sample standard deviation, S, or the proportion of individuals in a sample that have some property that would be our p hat. We can use all of those statistics, however, to understand what the value of a population characteristic should be. So the most common way that we learn about the value of a population characteristic is to study a sample. Every once in a while, we will take a census of our entire population, but most of the time it's simply unrealistic to do a census and get data from the entire population. So let's take a look just at proportions right now. Our sample proportion will be p hat, the population proportion will be p. So any quantity calculated from values in a sample, again, we're going to call that a statistic. And then what goes along with that is that the observed value of a statistic varies from sample to sample, depending on the particular sample that's selected. And you really don't have much control over that variability because these samples will vary. And so this variability gets the name sampling variability. Let's take a look at this issue of fracking to help us understand how this sampling variability works. So if you're not familiar, fracking is, at a very simplistic explanation, it's a process of injecting liquid into the ground in order to fracture rocks and release natural gas. This can also be used to release oil. But this process has allowed us, particularly here in the United States, to increase the production of natural gas. However, some people have expressed concerns that this process may have a negative impact on the environment. They don't know for sure that injecting liquid into the ground is a good thing for the environment, and so that leads some people to oppose it. So let's consider that we have a small population of 100 adults. Now, I know that it would be very unlikely to have a population that's 100, but in order for us to illustrate this idea of sampling variability, we're going to stick with a small population so that we can talk about it in more realistic terms. So based on a study done in 2015 by the Gallup organization, they suggested that about 40% of the population would be opposed to fracking. So in our sample, let's imagine that 40 people are opposed to fracking and then the rest of them are not opposed. So here, let's identify all of our population. So we're going to number them 1 to 100, and we can consider the first 40 as being people who are opposed to fracking, and then 41 through 100 being people who are not opposed to fracking. So again, this is our imaginary population, even though these proportions are consistent with the United States. So in this population, we have a proportion of 0.4 that are opposed to fracking. And now this would be a population proportion here because we are looking at an entire population of these 100 adults. Now, let's say that we don't actually know information about all 100 people. So what would we do instead? We would take samples. We would take a random sample of people from this population. We would calculate the sample proportion, and we would look to see what those values are and use that to help us estimate the true proportion for the population. So we're just going to do a little hypothetical here. If we were together in a group, we would actually run this simulation together. But imagine that we have the numbers 1 to 100 and we pick 20 of them. So you could also do this doing a random number generator and see what happens if you want to see how these samples would be produced. But imagine we pick 20 numbers 1 through 100. Now remember, people 1 through 40 are those opposed to fracking, and people 41 to 100 are those who are not opposed. So imagine that our sample would be these 20 numbers below. Now in red are all of the numbers that are from 1 to 40 and would represent people who opposed fracking. So in this case, we got 9 out of 20. And so that 9 out of 20 gives us a sample proportion of 0.45. Now that is relatively close to the true proportion of 0.4, but it's not exact. Now, if we were in a class and we all were doing this, perhaps we would get all of these different samples. So sample 2, you got 20 numbers, and in that case, only 5 of them represented people who were opposed to fracking. So that sample proportion is 0.25. Then sample 3 had 7 out of 20 for a sample proportion of 0.35. Sample 4 had a sample proportion of 0.4. They happened to capture the true population proportion, but then sample 5 had a p-hat of 0.5. Now, there's a few observations that we can make here. The value of a sample proportion is varying from sample to sample. That's our sampling variability. We also noticed that some of these samples had p-hat values greater than the real p, others had values less than the real p. And 3 of the samples, 1, 3, and 5, had sample proportions that were quite close to the actual value of the population proportion. Sample 2 was really far away. Now, imagine that we were to get another 45 samples, and so we had a total of 50 samples. And these would be the values that you would get for each of these 50 samples. We could put this in a histogram, and what you see in this histogram is that it runs from somewhere around 0.2, and the biggest value that we got was somewhere around 0.65. But you should see that most of the values were there towards the middle. The true proportion for the population is 0.4, and so that does seem to be about the average value that you would get out of these 50 samples. So we can consider that histogram as showing the behavior of p-hat. We took 50 samples and we plotted them, and we were able to see that most of these p-hat values were pretty close to 0.4, but every once in a while the values were really far away. So if you had happened to be that sample that was 0.2, you would think that the proportion of people in the population was not very high. Whereas if you had gotten that really large value of 0.65, you would have concluded that the proportion who opposes quite high. So this helps us see that if we were to take a sample size of 20 from this population and use p-hat as an estimate, we may or may not find a value that is really close to p. Maybe we do, maybe we don't. So that histogram shows us the sampling variability in p-hat. Okay, these p-hats are going to take a lot of different values. So we do need to recognize that we only took a sample of 20. And so this sample of 20 must not be quite good enough for us to be able to estimate the true proportion from our samples.